Hello and welcome to this demonstration slash calculation slash tutorial on how to go about calculating the values for the MOSFET, the diode, the inductor and the capacitor in a buck converter. So it's actually quite a straightforward process, but there are several design considerations that we need to look at once we've done it. And this Excel spreadsheet that I've written up here, it will go through and it will calculate the value of the inductor and the capacitor here straight off, and then it's fairly easy to figure out what the MOSFET and the diode needs to be specified to. But when we come to that later on, there are several things we need to consider. The current carrying path in the buck converter, it comes up through here, it's through the MOSFET, so we want the resistance between the drain and the source of the MOSFET to be as low as possible, so we're not going to have unnecessary losses here. And similarly, the inductors are not perfect. They do have an equivalent series resistance, so we want that to be as low as possible as well, so that way we're not dissipating too much heat from conduction losses in the MOSFET or current I squared R losses through the inductor. The other thing, of course, is the switching times to turn the MOSFET on. We want it to turn on and turn off as fast as possible. So in that way, that'll reduce the switching losses. And what my calculator does is later on, it will go through and it'll calculate all the losses and the efficiencies of the converter for the given values that have been selected under differing operating conditions. And that's done off screen. It's later on. So it's probably a good time here to point out that with all my Excel calculators, the input values are in yellow. So there's some input values we need to put in here and down here. The green is the results of a series of calculations, and then the blue is pretty much, shall we say, the answers. And what this one does, as I said, later on, it goes through here, it'll calculate all the ripple currents under different conditions and ripple voltages. That's what happens here. And then down here, it calculates all the power losses, the switching losses in the MOSFET, the I squared losses in the inductor, the conduction losses in the MOSFET, and the conduction losses in the diode. And then those are all summed up, so you get the total power losses down here. And then they're expressed as a percentage of the output, and then it'll work out the efficiency of it based on that here. So the reason these are fairly large tables is because all of these are done for differing input conditions. So here we've got a duty cycle of 0 all the way up to a duty cycle of 1. So we'll have maximum voltage at the output, and then here we've got from 0 current all the way down to maximum rated current. So if the thing's running at a sub-peak condition, say for example at only 60% of load and 80% of output voltage, for whatever reason the load's changing, we will know that the values we'll be looking at will be down here. So let's go up and have a closer look at actually how we calculate the value of the inductor and the capacitor, and what the requirements are to spec the MOSFET and everything like that. We'll zoom in so you can see what's going on here. That's probably going to be about far enough. So the value of the inductor. To calculate the value of the inductor, it's quite straightforward. We put the desired output voltage times 1 minus the duty cycle over the switching frequency times the ripple current that we would consider permissible. To calculate the capacitor, it's our permissible ripple current over 8 times the switching frequency times our permissible voltage ripple. So let's go and plug some numbers in here. We're going to assume that we're going to have 200 volts at the input, and we'll say that this is a fairly grunty buck converter. It's going to be delivering 15 amps, and the nominal output voltage is going to be 140 volts. So that gives us a duty cycle. 140 over 7 gives us a duty cycle of 0.7. And let's say that our ripple current, we're going to say we want it to be fairly low, so we'll go for, say, 0.7 of an amp. Our ripple voltage, we'll say we want that to be reasonably low as well. Let's call it as of 140, let's say we're going to have a ripple voltage of, let's say, 8 volts. and we're going to switch this thing at, let's say, 20 kilohertz. So if we go up here and have a look at this, we can see that the switching frequency that we've selected is inversely proportional to the value of an inductor, and similarly with our capacitor. So if we increase the switching frequency, we would reduce the value of capacitance that we would need and the inductance. At the moment I've got it set to 20 kilohertz. If we change it to 50, instead of having a 3 millihenry inductor, we would have a 1.2 millihenry inductor. And similarly with our capacitor, at 50 kilohertz, it's 0.22 microfarads. At 20 kilohertz, it's 0.55 microfarads. So we can see that if we increase our switching frequency, we will get better performance. We need smaller components. Smaller components are cheaper. But we'll just run with this just because, these are numbers. The whole purpose here is just to simply show you my calculator and show how we do these calculations. So to specify the size of the components, we've got our value of our inductor here and our value of capacitance here. Under this given condition, for a duty cycle of 0.7 and a maximum current of 15 amps, that's what we would need. What we would do is we would always specify our values down here to be the worst case. And in a buck converter, if we come up and look at the diagram, if the duty cycle was 1 and the output voltage equaled the input voltage, we would have maximum current flowing through our inductor. So we need to make sure that our drain to source current capabilities of this MOSFET are our load current, 15 amps. If the duty cycle was 0 and this was effectively turned off, this MOSFET needs to be able to handle a voltage across it of our supply voltage, in this case 200 volts. So let's pop back down over here, and that's what we have down here. Our diode needs to be rated for the full maximum current, 15 amps. Our MOSFET should be rated for our maximum current, our maximum perceived load current, 15 amps, and our input voltage, 200 volts. To get the value of capacitance for that given ripple voltage and ripple current, we can change that. We can by modifying these values here of our acceptable ripple. Now, if we wanted no ripple, then our values here are going to be really big. Let's go up and have a quick look at that. So let's say, for example, we wanted a ripple current of 0. It's going to fail. So let's put in, say, 0.1, just because whenever you start doing zeros in calculations, you have problems. And say 0.1 volt there. So we need a really big inductor, 21 millihenries, and a 6 1/4 microfarad capacitor. Again, pretty large. So if we just go back, put some sort of more realistic numbers in, around about 10% or something like that, the current there, let's, what I say, we'll have it at being 0.8 of an amp, and the ripple voltage, we'll call that, we'll call it 12 volts. So here we are here. We've now got these values. Now, these values which it gives us to get that particular ripple are not available. We cannot get a 0.417 microfarad capacitor or a 3.125 millihenry capacitor. But what we can do is we can get one that a fairly standard one. So if we look at 0.417 microfarads, what capacitor values are available? 0.417 microfarads. So we could go for a 0.33 microfarad or a 0.47 microfarad. Well, let's go up a little bit and we'll go for a 0.47 microfarad capacitor. 0.47. There we are there. And for our inductor, it says a 3.125 millihenry inductor. So 3.125 we can't get, but we can get a 3.3. Here it is here. So we'll go for a 3.3 millihenry inductor. These are standard values. Now, as I said before, no inductor is perfect. They all have an equivalent series resistance. And I'm not going to look at a real inductor, but if you go and buy one or look up any of their spec sheets, they will tell you this. And we'll say that, for example, that this inductor has a 50 milliohm equivalent series resistance. I'm just picking numbers here. Right. Now, diodes, our diode that we're going to get, our diode which needs to be rated for 15 amps, is not going to be a perfect diode. They all have a volt drop across them. And in order to handle 15 amps, you're going to need a fairly chunky diode. And so we can expect it to have a reasonably large volt drop across it for it to be able to handle that 15 amps and to be able to block the full 200 volts. So I'm just, for the purposes of this, it's going to be more than your 0.7. So we'll go for, we'll call it a 1 volt drop there. And the MOSFET that we are going to choose, that we need to choose, that needs to be able to handle our 15 amps and our 200 volts, it's going to have a resistance between the drain and the source. And I'm just going to pick a number here, and we'll call it 125 milliohms. And they don't turn on straight away. They don't turn on perfectly. So if we make an estimate of the presumed time it takes to turn it on and the time it takes to turn it off, and if we call that, say, 75 nanoseconds. Now, what we can then do is we can go through and see how does our buck converter with these realistic values, how does it actually perform? So the previous equation that we used to find out the value of the inductor, we can rearrange and solve for the ripple current. And the equation we used up above for the value of capacitance, we can rearrange and solve for the ripple voltage. And then what we can do is we can go through and we can put these values in for differing values of K, and for differing loads, we will get a differing ripple current, and that's what we've done over here. And similarly with the ripple voltage, for a differing value of the voltage, we will get a differing value of the ripple. So let's look over here. For the ripple current, based on K, we will get these values. And then when we make it, when we change our load that we're going to draw, we're going to see that the differing value of ripple is going to be quite significant. And this is what my calculator shows here. It does the same sort of thing over here with the voltage. We can see that in certain situations, we actually have a very large ripple voltage of 50% down here when we're running at a 20% and a duty cycle of 0.5. We can see we actually get a very large ripple voltage. So if we carry on down, we can look at the power losses. So the switching losses in the MOSFET can be found through its being a product of half times the voltage drain to source voltage times the current through it over with the total turn off and turn off times the switching frequency. I'm not going to go through the derivation of these equations, just take it that they exist. And we can see here that the losses, the switching losses in the converter are going to be increase as the current goes up. As the current goes up here, when this is a constant, the switching frequency is a constant, the drain to source value is a constant, 0.5 is a constant. The only variable here is the current. We can see that if we were to take this buck converter up to full current, drawing the full 15 amps, we can see that the switching losses in the MOSFET alone are 2.25 watts based on those values that we chose. Similarly with the inductor, the I squared R losses, the value, the power loss in the inductor is I squared R. R doesn't change. That's the equivalent series resistance of the inductor. But the current does change. We can see here that under these conditions here, our inductor is actually going to be dissipating 11 watts. That's quite significant. It's starting to get up there. Our inductor could be starting to get a little bit warm there. Now, the conduction losses in the MOSFET is found by the current squared times the resistance through the device, the RDS, times the duty cycle. And so the duty cycle is one variable here, and then our change in load is another variable here. And so we get this table of data. And we can see here that when the buck converter is drawing maximum current and at maximum output voltage, the conduction losses in the MOSFET are 28 watts. Again, quite significant. But if we ease the machine, if we ease it back and we only start drawing, say, 9 amps out of it, and we're only going to be drawing at 140 volts, when we would end up only having 7 watts being dissipated through the conduction losses in the MOSFET. Now, similarly, the expression for in the diode, the power loss in the diode is the output current, which is one of our variables, times the forward volt drop, which is not variable, and our duty cycle, which is, so here we've got our duty cycle across the top again, our current, and again we go through, and I've done all these calculations here, and we can see that when the duty cycle is very low, the diode is doing far more work, and we've actually got significant losses down here through our diode. So we can see here that depending on how the buck converter is being operated, our losses are varying quite a bit. Now, if we go through and we add all these up, this is what we've got down here. Under these particular conditions, our buck converter is at, say, an output voltage of 100 volts at, say, drawing 7.5 amps. It is losing 11 watts. At full noise, when it's running flat out, maximum current, output voltage up to a maximum, it is losing 41 watts in it. 41 watts is, that's reasonably significant. Bear in mind your standard incandescent light bulb that you'd have in the bathroom is, about 60 odd watts. So this is 3/4 of a light bulb. It's quite hot. If anyone who's gone to change a light bulb will know. Now, what we've then done is converted these losses into a percentage of the output. And we can see here that when it's operating at full noise, whilst it's got 41 watts of losses, it's only 1.4%. There are certain situations where it is greater, like, for example, our losses down here, when it's operating at 40 volts on the output and 9 volts being drawn through it, our losses are 4%, which is much more than 1.4. So just because we're operating our buck converter hard up here doesn't mean our total loss, our percentage losses are greater. Down here, the buck converter is much less efficient down here with a lower duty cycle. Once the duty cycle starts getting up, then things are starting getting better. And this is mainly due to the power losses in our diode, if we were to go up and look at that. But just take it from me on that one. And then over here, we've got the overall efficiencies of our buck converter. We can see here that up in this high load condition, the buck converter is very efficient. We're looking at 98%. And then down here, under these conditions, high current with low duty cycle, the efficiency falls right away down to 90%. So that's my buck converter calculator. I can go through and I can change values and do a little bit of pokery, and it will go through and solve a lot of things for me, and I can change the values. I could maybe take the values for a different MOSFET and put them in and see how does that improve or maybe get worse for my buck converter, or different diode values. And it's the diode ones. Your diode is where most of your inefficiencies are, particularly in the low duty cycle. And this is quite important actually, because as I said, if you're driving a motor, when you start the motor up, you will be operating at a very low duty cycle because you'll only be putting a low voltage on a DC motor. But because of the inrush current into the motor, you'll be drawing a large current. So when you first start the motor up, Your buck converter is at its most inefficient, sitting down here at about 90% efficiency. If we go back to our previous example down here, when we first start this thing up, we're losing 30 watts at max, if it's going to be drawing significant currents at the low duty cycle. And even though we might be pulling very little power out of it because it's only starting up, we're dissipating quite a lot. And then as the machine runs up to full speed, the efficiency, the losses increase slightly, but the total losses through it, the total power being delivered, are significantly larger. And we see that here. Our losses go from around 10% losses at full current down to, when the machine's up and running at full voltage and lower running current, we've got efficiencies down around 0.3%. So we go from losing 10% to losing 0.3%. And this is probably the arc that we'd be going through if we were using a buck converter to drive a motor. We'd be running it through here somewhere. So another little bit of a divergence on the end there. I hope you understand what we've been doing here, and you've got something out of this. As I said, those are your main equations up the top here that you need to understand in doing it. And then down here, this is where how you specify your MOSFET devices. And then you've just got to take those off to your various suppliers and your data sheets, and then just go and pick a device that will meet your criteria. Bearing in mind, you want these values here to be as low as possible. You want a low equivalent series value in your inductor. You want a low volt drop across your diode. You want a low RDS in your MOSFET, and you want a fast turn on and turn off time to reduce your switching losses. Thank you very much for watching. Go forward and design your buck converters with pleasure and joy. It's always nice when they work. And we'll see you later. Thank you very much.